Hello and welcome back. In this video, we'll be working through an example of showing that a limit of a function of two variables does not exist. So I'm telling you right off the bat that the limit does not exist. The more advanced problem is I just give you a limit, ask you if it exists or not. If it exists, I have you find what the limit is. If it doesn't exist, I need you to show me that it does not exist. So that's what this video is for, is giving you methods to try to show that a limit does not exist. All right. So why is it that this limit is maybe not existing? One thing we might try first is just figuring out what the domain of this function is. So what's my domain? I need the bottom to not be 0. So I need, not ready to write the domain. So I need x squared. I want to find out when x squared plus y squared is equal to 0, and then exclude that from the domain. But here I have a square, two squares of real numbers added together, so the only way this is 0 is if both x and y are 0. So this implies that x equals y equals 0. And so I just need to remove the point x, the point 0, 0 from the plane, and that'll be my domain. So the domain is the set of all points x, y in R2 such that x, y is not equal to 0, 0. That's my domain here. And so it really just looks like we've taken the plane and removed the origin from it. So I have that graphed down here. Here is my domain. All right, so everything in the plane except for, so I've just drawn an open circle here around the origin. We're just excluding the origin. So this is what some call the punctured plane. We've just removed a single point, the origin. All right, so how do we show this limit doesn't exist, or what would we be doing if we were trying to evaluate this limit? Well, remember this fact that if the limit exists, then the function values approach that limit along any path in the domain to the point 0, 0. So this allows me to, if I think of the negation of this, this tells me that if I can find two paths such that the function values along those paths do not approach the same number, then the limit does not exist. So this is what I want to do. So find two paths that approach, I'll say two paths through the origin, through the point that we're taking the limit at, through 0, 0. Let me say if we can find, so I'll say if we can find two paths, two separate paths that go through the origin such that the function values do not approach the same number for each of the paths, then the limit does not exist. So that's our goals. We're going to find two paths that go through the origin that give us different values for the limit, and therefore the limit does not exist. Compare this to, say, in Calc 1 with functions of a single variable. The idea there was to compute a left-sided limit and a right-sided limit. If those two were not equal to each other, then the limit didn't exist. So this is the two-dimensional analog of that. It's not just left and right, but rather if we can find two paths that do this. So one sort of standard thing you could try, this is a good first thing to try for showing a limit doesn't exist, and that is to try lines. And since we're evaluating the limit at this boundary point at 0, 0, we're going to try lines through the origin. If we were doing it at a different point, we would consider the lines that go through that point. So we're trying lines that go through the origin. And so those look like y equal mx plus, our y-intercept. But since we want this to go through the origin, the y-intercept would be 0. So it's lines that look like y equals mx. So for various values of m, we can consider a line through there. So that's the idea. Is we'll consider, so this would be the line y equals x. Right, we can consider that line as we approach the origin from the right or from the left. We could do y equals negative x. That's also a valid option. We could do things with steeper slopes. more gradual slopes, right? We have a lot of different possibilities for lines through the origin. So I'm going to do this first by just computing, just to show you how, like how to write a limit, how to compute a limit along a path. We'll just do along y equals x, and then y equals negative x. We'll see what happens, and then I'll show you how to do this in general to consider a limit along any line that goes through the origin, sort of all at the same time. So let's compute. I want to compute the limit as xy goes to the origin. And I'm going to say here along y equals x. So that's how we write this. Along y equals x of the function x plus y squared over x squared plus y squared. So the idea is I'm going to, along this curve, if I replace all of my y's with x's, because we're along the curve y equals x, any point on that curve has y equal to x. It means I can replace all my y's with x's in this function and reevaluate. I'll just have a function of a single variable, and then I can do a regular old single variable limit. So that is, this is the limit of, so here I'm going to replace y with x, so x plus x squared over x squared plus x squared. Now I do have to think for a second, how do I get to the origin along the line y equals x? Well, if I let x go to 0, then y will go to 0, and xy will go to 0, 0. So here I want to send x to 0. I have to do a little bit of thinking there to make sure that this limit as x goes to 0, implies that the point goes to the origin, our original limit. And now we can just do some algebra here. We can evaluate this limit of a function of a single variable. So there I have 2x in here, squaring that, so that's 4x squared. Down here I have x squared plus x squared, so that's 2x squared. And now I can use all my usual tricks for functions of a single variable and computing their limits, right? I can cancel these x squareds. I get 4 over 2, or just 2. Cool. Let's try another one. All right, so what this means is my function values are approaching 2 as we approach the origin along the line y equals x. So if you imagine, here's my line y equals x. Imagine this this line up on the surface of my function. As I approach the origin on the surface of my function, I get to just the value 2. So what happens if we approach, say, y equals negative x? So let's do another one here. I'm going to compute limit as xy goes to 0, 0 along y equals negative x. So same type of thing here. And we're evaluating it of this function, squared plus y squared. And now, again, as x goes to 0, y goes to 0, and we go to the origin. So I'll send limit as x goes to 0. Up top here, I'm going to have x plus negative x. That's going to be 0. And then I'll have x squared plus negative x squared. So substituting negative x in for y. All right, well, that's a limit as x goes to 0. Up top, I just get 0 over, here I'll have x squared plus x squared over 2x squared. Excuse me. And so that will, this is just the 0 function, this just goes to 0. Cool. So along the line y equals negative x, so up on my function, the surface of my function, if I'm along this line y equals negative x, as I go to the origin, my values approach 0. Right? So as I go this way, I approach 2. If I go this way, I approach 0. So that's very strange behavior. And what that means is that the limit does not exist. So because these limits differ, the limit does not exist. So that's how we can show a limit doesn't exist. All right. Now, thinking about generalizing this, working other problems like this one. One, how did I know? So maybe if I didn't say the limit didn't exist right at the beginning, how would I have figured out that the limit didn't exist? There's no one way to do that. But rather you can look at the structure, right, the algebraic structure here of this function, and recognize that even if I square this top part out, I get what, x squared plus 2xy plus y squared. I wouldn't be able to cancel anything off. So kind of just by looking this, there's nothing to cancel. Doesn't look like I can cancel anything. Right? It doesn't look like I can remove this part of remove this this hole in the function. Doesn't look like anything cancels, so that kind of clues you in that the limit might not exist. So that's something to look for. And then once I've sort of figured out that, oh, maybe I think the limit doesn't exist, the idea is to look at, all right, we got to try different lines that go through the point. But actually, we don't have to try lines. It doesn't have to be lines that we try. It's not always this family of paths that work. In fact, we'll see an example where if I consider any line through the origin, I'll get the same limit, but yet the limit doesn't exist because there are other paths, right? The family of lines, this is not all the paths through the origin. You could also say approach the origin along a parabola. So a parabolic trajectory through the origin, like this or this, or even like this. We could approach along one of those parabolas, and maybe those don't have the same limit along those paths. Or maybe we need to try an even crazier path, maybe some kind of spiral shape that goes into the origin. When I was in grad school, that was one problem. That was the thing that worked. We needed to consider different spirals, parameterized polar, like in polar coordinates that went to the origin. So sometimes you need to try different things before you can finally show that it doesn't work. And so to aid us in that, it's sometimes helpful to consider all of the paths in a family at once. So I want to show you how that works, because I don't have to just pick two m values, right? I did y equals x and y equals negative x. I could say do all the lines at once. So how do I do that? Well, we just say we want to do the limit as xy goes to the origin, and I'll say along. This is one of the beautiful things about math, is I can have arbitrary constants, right? This m could represent anything, and I'll just keep it as m throughout the whole thing, and then at the end, consider different values of m. And we're doing here x plus y. We'll still do x plus y squared over x squared plus y squared. So what happens when we, again, as x goes to 0, y will go to 0, and the point will go to 0, 0, and now I'm replacing y with mx. So I'll get x plus mx squared over x squared plus mx squared. All right, so what does this give me? Let's check that out. Limit as x goes to 0. Well, let's see. Up here, I have 1x plus mx, so that's m plus 1x, and that's being squared. So this is m plus 1 squared times x squared. On the bottom here, I'm going to have m squared times x squared, and then I have another x squared, so that's m squared plus 1 x squareds. I can cancel the x squareds off, and now I'll just have limit as x goes to 0 of m plus 1 squared over m squared plus 1. As x goes to 0, well, this is just a constant, so this is m plus 1 squared over m squared plus 1. And now we can just plug in different values of m to approach along these different lines. So let's say we did m equal 1 first, right? We did along y equals x. So if m equals 1, this top goes to 2. Square that, I get 4 over 2. I get 4 over 2 or 2. If m is, we did negative x the other time, so that was an m of negative 1. I get a 0 on the top and a 2 on the bottom, so I just get 2. I can now try other things, right? I could try m equals 0, in which case I'll get 1 squared 1 on the top and 1 on the bottom. We'd approach 1 there. And so you can try all different values of m, and actually you can see by this equation, or this function of m, that this is not, this changes, right, with respect to m. It's not constant with respect to m. It actually changes around, and that's how we can identify that the limit does not exist, sort of really quickly all at once. Or say if we're at if we really suspect a limit doesn't exist, we could try all the lines, and maybe it turns out that they're all the same value. Maybe this really is constant with respect to m. That informs us that maybe, one, either the limit exists and we have to try harder to cancel something out or go to the definition of a limit, or two, we need to consider a different family of paths that go to the origin. For example, parabolas or other curves that go through the origin. Maybe different powers of x, maybe x cubed or x to the fourth, something like that, right? Okay, so last thing I want to do with this video, this is how we show a limit doesn't exist. I want to show you what's going on with the surface of the function, like what's actually happening, so that if I approach along y equals x, that's different than when I approach along y equals negative x. So what is the surface, what does the graph of this function look like? Well, here I have it graphed in one of our interactive figures in the textbook. You can play around with this yourself. It's like we pinched the plane, right? Doesn't it kind of look like we just pinched the plane? This is a really cool function that acts like this. And we just kind of pinched the plane there. So first, this blue, so the green line, if you can see it, it's under the surface. That's my path in the xy plane, right? That's approaching 0, 0. And then I have the function values along that line in blue. So let me maybe try and get a better view. I have that along the line, the blue one there. And as you can see, right, it's just 2. It's a constant 2 along that line, it sort of looks like. And it approaches 2 as we approach 0, 0. Compare that to, let's say, y equal negative x. And now my line's down here, right? It's down on the xy plane. And same with the function values there. And now as I approach the origin along that line, I'm at that base of the pinch, and my function values actually approach 0 there. Isn't that neat? I think it's really cool. I think this is a fantastic function. We can try other values of m, so maybe m equal to 2, and we compute that. We would have got something like, I think, 9/5, I think, is what we get if we approach along that. Or we could go -2. We're going to get a little bit different, right? It's raised off of it a little bit. So we can try lots of things, and we get a bunch of different function values as we approach, right? Oh, maybe you can see that there, right? I'll get different things. So that's what the function looks like that causes this strange behavior. So a little bit of a geometric explanation for you, as opposed to the algebraic explanation here. So that's another thing you can try when I just give you a limit. You can try graphing the function and see if something weird is going on at the point that we're taking the limit at, right? Actually look at the geometry and see if something funny is going on, and then execute with the algebra. All right, that's it for this video. I'll see you next time.